Okay, so we can start. The chairman.
Good evening, everybody. I welcome you all to Professor Andrea Vinante's tutorial session. Sir.
Okay, thank you. So, well, for this tutorial, well, the idea is that I would like to go more in the detail or discussing more in the detail some of the issues that related with the experiment I described today in my presentation. So I got some questions from people, and so I have a list of possible things that I could do, but maybe if you have some questions, special questions, we can start with, if you have any issue, special issue related with the presentation, with the experiment, in particular, this Cantilever experiment, which I showed this morning. Otherwise, yeah. So, well, maybe I can, okay. So for instance, well, this is the system essentially. It's just the cantilever. This is, oops. This is the vibrational bending mode of the cantilever. And we have this sphere here. And one of the questions was actually how we go from the measurement. So in the measurement, as we have seen, essentially we measure, well, the output of the experiment is essentially this one. So what we get is that the maximum, for this experiment, then we can go to the other, but the maximum increase of temperature due to any, let's say, external unknown force noise, which is not non-thermal, is less than 2.5 millikelvin for this system. And from this, we want to go to upper limit, to derive an upper limit in the parameter space of the CSL. Well, you mean to characterize the system? Because how I induce the motion? Well, we can do it just by driving with a piezo driving. If you want to, for instance, to measure the quality factor, we just excite with this piezo and measure the ring down, the decay time, and from this you can measure, for instance, the quality factor of the system. But these measurements, of course, are done without driving because we are measuring the fluctuations of the system when it is undriven. So one thing was how do we go from this to the exclusion plot in the CSL parameter space? I don't know if this was clear, which is actually this one. So this is the thing that is interesting for the CSL theory, but the experiment is just this. So the experiment just keeps this number, this relation. So you know that the maximum heat in the system from maximum increase of temperature cannot be higher than 2.5 millikelvin. So this was the answer. So we calculate the heating as a function of the RC, the model. And we get this, this curve. Here we have two contributions from the one from the sphere and the other from the cantilever. So this is clear. This is calculation just applying the theory of a CSL model. We fix lambda in this case, which is 10 to minus 6, 17 hertz. This is actually the value, the lowest value that you can find in literature, which is the original one proposed by Gerardi Rimini and Weber. And for this lambda, we get this heating in our system as function of RC. If you change lambda, of course, this scales with lambda because remember in the formulas of the CSL, the lambda is multiplying the noise, and then the increase of temperature is proportional to lambda. So if I can write that delta t is just equal to some function of RC times lambda, where this function is exactly this one, the shape which was calculated by Angelo and his student. It's postdoc actually. And then we have, this is the theory, and then you have the experiment that the t is equal to is less than 2.5 millikelvin. So we just combine these two and to get an upper limit. So this means that just this function times lambda, just 2.5 millikelvin, or that lambda is just larger than this. So this is quite trivial in the end. So in fact, this somebody asked why this shape, all the curve that we got from the other experiment also have this shape. And so there is a minimum here, and then it's quite a simple, like triangular shape. And the reason is just that this one, which is related with the fact that this heating rate you get from the model is maximized, and when the size of your system is comparable with this RC. And from this to the upper limit, you get just well, the curve is the inverse of this one, and of course rescaled to the lambda. So in this way, just so I think it's clear. I don't know, is it clear? This point. If you have questions, just. Please ask. Any? Why? Yeah, this is, well, this comes from the model. so here I show also this maximum. Well, essentially, the theory predicts that this increase of temperature due to CSL is contains some parameters of the resonator, but then you have this diffusion factor, which is this bloody integral, and lambda is actually inside here. This gamma is proportional to lambda in the CSL. It does not appear here, but yeah. So lambda. Okay. So yeah, the lambda appears linearly in the heating, so you can factorize in this way, and then it is quite easy to convert this heating into a measured the upper limit on the upper bound. Experimental upper bound is delta T. You can directly convert into an exclusion plot in the third parameter space. Okay, this was an issue. I got other questions. Well, most questions were actually related with the other experiment, in which we measure actually this excess noise. Which was this one. A bit. So well, the experiment was very similar to the other, and in this case I have simply a cantilever moving above a squid, and we measure the position of the cantilever by measuring the flux which is coupled into this squid, and the squid converts this flux into a voltage. So you have direct measurement of the displacement of the cantilever. And so you measure the noise as a function of the temperature, and you get this curve in which I plot this quantity, which is the amplitude of Lorentzian you get from a fit. And this quantity scales with P over Q, which is what you expect from thermal noise. But as we see, this doesn't go to zero as you expect it if you have only thermal noise in the system. So it seems that there is something inside, some unknown force that is driving the system in addition to the thermal noise. So from that, we actually tried to figure out if there was something, and I actually excluded some possible options. So one of the things that the questions I got before, let's say, well, one was this. So one of the options, one of the possible options for this to explain this noise is that actually the cantilever is not thermalizing well with respect to the thermal bath. So we have an experiment where we have somewhere this cantilever. Well, the experiment technically is done well. you have a squid. It's just as seen from side. So this is a ring, actually. Okay. Then you have this cantilever here, which sticks out from tip. And this moves up and down. So there is magnetic moment, and this couples magnetic field inside, magnetic flux. So one of the points was that the temperature of this, that's called T, is different from the temperature of, for instance, let's say, this chip is actually, it should be thermalized because I bring some metal piece here from, let's say, from the copper box. All these things inside the copper box. It is well thermalized the temperature of the dilution refrigerator. So you can say that this thing is easier, you know. But then the dissipation, the thermal noise comes out from dissipation. But where is this dissipation? The dissipation is likely inside the cantilever. So we have, could be due to coupling to phonons, to localized excitation like two-level systems. Most likely is something that is due to the bending of this cantilever, which stores some elastic energy inside. It's silicon. Yeah, so I agree. The dissipation here is mostly due to either to level system or to surface dissipation. So if you have something, some dirt or some piece of anything that you can, or even the oxide that forms naturally on the surface, when you have the bending, you can have some dissipation. But so the idea, well, you can also have a dissipation somewhere in the magnet itself. There is actually a magnetic field here, at least the ground, the Earth magnetic field. And let's assume that the Earth magnetic field is like this. Then when this object moves, you can have dissipation due to the motion of the magnet. Okay? The particle. What the material? This is ferromagnetic material, is actually an alloy of neodymium, hard ferromagnetic material. You mean? You want to calculate what the? I mean, yeah, yeah, yeah. But that, yeah, from CSL model you can calculate, but yeah. So the only thing you can do for the CSL is say, well, I assume that is CSL. And then from the number I get, I can say CSL is in this point, on this line in the parameter space. But here I'm actually thinking that there is some other explanation for this noise, right? What if it is coming from CSL? Well, that will. CSL is a possible reason because it's compatible, right? But this is just a speculation. So if you want to claim that this is really CSL or anything exotic that looks like CSL, so that's what I want to do actually is try to understand if we can find an alternative explanation, right? And so if you have any alternative explanation that you can. Yeah, I should go back. The delta T depends on, you mean the geometrical parameters or? Well, there is a ratio between the radius. It's a function of the ratio between the radius of the particle and the RC of the model. Then you have other parameters of the resonator. Yes, you can. I mean, if you are really looking, if you really want to probe with this CSL, you have to change some parameters. That's. Yes, you have to change the cantilever essentially, or you can change the mass of the particle. You can change the density. For sure, I mean, depends on what is more, one thing is more likely, but yeah, sure. If it is a fundamental effect like CSL, then you have to change the parameters in such way to test the dependence of this effect on the parameters. And so there are, well, we can see what it's possible to do. Then you have to look at the formula. Well, assuming that we are doing an experiment, the same experiment just by changing the sphere, for instance, what can one do? This is the dependence of the eta factor on the sides. Here, well, what we have is the constant of the model. We have this geometrical factor, which follows basically this shape. And then the only other important parameter which enters this formula is the density square. Well, actually, here you have the density square, but then the total effect will depend on the mass here and the frequency. So assuming that we are changing the particle, use a particle which has a different density and a different size, then well, it's not so straightforward to see what happens because you have, well, you change the mass here, you change the radius, but you change also the frequency. So this, but you can probably play with the parameters in such a way to get a change to move in a different region of the parameters. So let's say you can enhance the effect or depress the effect. Probably the most efficient way is to increase the density. If you can increase the density by keeping the same mass, then you would actually, but it would move all through this. So that's not so clear to see what happens, but probably you have to do something like that. You do one experiment, and then, like this one, assuming that this CSL, you have this kind of curve. Then you change your experiment, you change the parameters, and you could get something like this, because it changes the size of the part. Then two measurements will already find this single point. It means that those should be the parameters of the CSL. Then if I make a third experiment, I should also get something here. Like here. So if I do n experiments, I finish, and I end up always here, then well, maybe one can start believing that this is CSL. Is it correct? So yeah, in principle, experimentally, if you believe that there is really an effect, that it could be, you could get some kind of confidence by doing, by repeating the experiment in such way. At the moment, I'm more concerned that this is just some spurious effect of any other kind. So what my initial question was, can we try to actually find a good reason, not related to CSL, to explain this effect? And well, in the end, you have to do the same thing. You have a model, and then you change your parameters in order to understand or to rule out some possible explanation. That's what you do in experiments usually. And yeah, one of the options that I actually proposed, I tried to figure out, and I actually excluded, but it's not completely ruled out. It's just not, to me, it seems not convincing, but what I wanted to propose you to discuss was this heating effect, which, so I show you tomorrow, this morning. This last option so the idea is can be that the cantilever itself stays at the temperature which is higher than the thermal bath, in such a way that when I cool, when I reduce the temperature, somehow the there is some residual gradient which survives. So I actually observing thermal noise, but the temperature here is not the temperature of the thermal bath, which I measure with the thermometer, but it's actually higher. And the reason why I excluded this assumption is that this should lead to something like that. This is the previous experiment, so it's short, in which we saw this nice linear behavior, and at some point, all of a sudden, this point deviates from the partition line, and this is an effect which you can model, sorry, and I would like to go more into the detail of this. And it's actually what you actually expect when you have some kind of overheating. So in this case, you expect some kind of overheating. Why? Because you have a squid here, you have this magnetic particle here, and then you have this cantilever. This cantilever is long and thin, and there is a finite thermal conductivity through this cantilever. So if there is any source of power which is dissipated inside this magnet, for instance, then you will have to dump this energy, this thermal energy, and the only path is this, because there is no gas inside, so there is no thermalization to the gas. The temperature is so low that there is no way for the system to cool by radiation, by thermal body, black body radiation. The only way to cool a system at temperature is by conduction. So in vacuum. So if there is some power dissipated here, there is a power that flows, and since there is a finite thermal conductivity, there is a gradient. So you have the temperature, the particle will be larger than the temperature of the substrate. So in principle, this might explain why here we see why in the data here we see some finite. Yeah. So the point is that exactly we would expect this. Why we would expect something like this and not? So in this case, we see a saturation. And I think it's precisely because of something like that happens. And we can actually explain this, this curve. So because that depends entirely on the thermal conductance of this guy. So basically, let's suppose that you have a power here. And then you have a conductance, which will depend in general of the temperature. So the material here has a thermal conductivity, and it is well known from, well, probably you should know also that how is the dependence of the thermal conductivity of a crystal, of an insulating crystal at a low temperature? What do you expect? That some condensed butter stuff, the body knows. Well, it goes typically with the cube of the temperature. So if you reduce the temperature, any material shows a thermal conductivity which drops very quickly with the temperature. This holds for insulators, but for metals, you have a linear dependence. That depends on the fact that in metals, you have electrons. which conduct heat, while in insulators you don't have electrons. So the only path is the only mechanism which you can use to transfer heat is through phonons. And the density of phonons scales. We have this dependence on the cube, which comes out. So if you have this kind of system, you can make it more clearly. You have just, let's say, a system and temperature T, and then you have the thermal bath, and then you have this thermal conductance, or the inverse, the thermal resistance, and then you have a power here that goes in. So if you do this simple model, which is a reasonable approximation of this system, then well, you can see what you can calculate how much is the temperature here compared with once you fix the temperature of the thermal bath. You could do this calculation is easy in the sense that you will have that some power. Well, the total power that flows through this system is suppose that this is just the thermal conductor. So the relation between just the Ohm relation for the heat. So power so in each point you have what you have to do is actually approximating the system in this way. So you have a heat here, this temperature is T and this is tau, no? And since the section is always the same, you can assume that there is a thermal conductance, which is the same in any point, but except of the depending on the temperature. Do you agree with this? I assume that there is a flow of power that flows through the cantilever, generated here, for instance, which is the most likely situation. So can we calculate calculate the thermal gradient across this should apply the definition. But also, if you have a flow of dt here, the gradient of dt in a layer z is the coordinate, then you will have what is the definition? You have a power. This power has to flow at any in any point. This W. Where? This is another point. But I can tell you that a squid could be the source. So the squid is actually, I tell you that there is Josephson oscillations in the squid. So when the squid is working, there are actually currents that flows into this. This is a ring, right? And this ring current actually generates a field. It's a microwave field. And this particle is actually, well, it's a magnetic particle, but it's also actually has also finite conductivity, electrical conductivity. So if you have a magnetic field which is oscillating in a metallic material, then you have a dissipation. Well, actually, I did the calculation. This is a bit complicated to, no, not so complicated, but you can do. So given electrical conductivity of this material, you can calculate actually the power of this. Typical. In this experiment, I think it was roughly 50 microns, while this is 20 microns. The size of the squid is 20 microns here. Yeah. This is something like 50 microns. And this is roughly 20. So there is some field that reaches the particle. A microwave field, this is so highly oscillating, and this dissipates some energy. You can calculate this. You can, knowing the size and the electrical conductivity, you can easily make a model, and you can get the power that is here. This power is something like with reasonable values for the amplitude of the current, which you can estimate. Something like 1 femtowatt. So something like 10 to minus 15 watt. And this power actually is there. So I know that there is some dissipation here. So I know that there is some thermal gradient. That's why I took this seriously, because that could be actually one of the possible options. Now, what I wanted to do, try to model the system to understand if we can understand what will be the behavior we expect, and this, which should be actually something like that. Is it clear? No. Okay. Yes. Not you, but your group can probably do it. You don't need a motor here. You can just do it without. It's a much simpler experiment. And this experiment, everything is aligned. So So we can try to go back to this fundamental problem. I see if we can do it. So the definition of what is the definition of thermal conductivity or thermal conductance? It is essentially this, right? So the power that flows through elementary element here, infinitesimal element, is proportional to the gradient of the temperature through the thermal conductivity. And if you integrate this I don't remember how to do it. It depends on temperature, so we have like each point here has a different thermal conductivity, but it must carry the same power. So what we can do is something like this. Any idea how to solve this? What I want to understand is how much is the difference in temperature between here and here. It should be an elementary problem, but I can actually do it just like this. Then we can just integrate. So we have the power times the length equal to the integral of the conductivity times which is exactly this, but with so if you do this integration and you take into account that the thermal conductivity depends on the temperature, you get that this is something like A cubed. A is the constant of proportionality we have here. Sorry, do you see anything there? Well, I go rapidly to the point. If you do this integration of t cubed, you get something like t to the fourth minus t naught to the fourth divided by 4. It's just a stupid integral. And what is the point that I put here? That if you do this model, you get this relation, which is t to the 4 minus t naught to the 4 is equal to some constant, which is proportional to 4. Yeah, it's some constant which is proportional to the power. Divided by 8. So that's okay. That's the whole thing. So what does it mean, this relation? It means that if you have a power dissipated in here, as I said here, you expect the gradient to follow this relation in which you have this fourth power in this term. If you write the dependence of T on T no, it's equal to this constant times the power plus no to the fourth multiply to 1 to the fourth. Okay. So how does it work? This is exactly giving that saturation, because you have something that when you are at high so we change, in this case, we have this T is actually the T node, the temperature we measure with the thermometer. T is the temperature of the stuff that dissipates, so the thing that is on the Y. So what we see here is T node to the fourth plus a constant, and the entire thing is to the power 1 to the 1/4. Which means that when this fourth power is essentially, if you try to plot this function by changing the exponent here, you will find that you gradually move from something that is smooth to something that is very sharp. So already with the 4, the function of 4, you get, if you plot it, you get really something like this. You can try to plot on, but it's quite intuitive. Because this fourth power kills, when this is larger, when this number is smaller than this, you have a constant. But this exponent somehow makes the transition very sharp. Okay, so that's the reason why I think, well, this data there is it's very unlikely that this is a lifting effect, because I see a linear behavior very clearly on the orange, and so this should not give, this is not what I expect. So the point is, for when the temperature here is larger than this is approximated always, when this is just larger than this becomes already something like a straight line to 0. So this is the node. So as long as I don't see any saturation, it means that I am in the regime where I'm above the saturation, which means that I'm not seeing effectively I cannot, so I'm not seeing a effect of the power, of an external power. Actually, for this experiment, I did a calculation. So I'm pretty much sure that if I go below the temperature, at some point I will see some saturation. Because at some point you will have this. No, it will not. So this intercept appears, the point is that this intercept appears by fitting the whole line, the whole range in which we don't see saturation. So we are actually here. And this curve, even under this effect, is approximated by this. It's just a straight line to zero. So yeah, then we need to know this constant A. We need to know the geometry. Well, yeah, it's possible in principle, but somebody has to find out the value for the thermal conductivity of silicon at the temperature. The thermal conductivity of silicon at cis silicon at low temperature, and then it's possible to do an estimation. This is the diameter is the radius is 15 microns. The radius. So this green data refer to different measurements, so maybe it makes a bit confusion. So let's go to, okay, this is the consistent set of data. Those data were done at different couplings, so maybe it makes confusion. So what's the question? What do you mean? Which point? Yeah, this? Well, within the error bar, they are consistent. course, it can be some systematic effect, but what kind of systematic effect are you meaning on the? So you are arguing that these 2 points are not consistent, or they? That was the original question. But within the error bar, these are consistent. I'm sorry, at this point, these green points, I just superimposed over the blue data point, but without the error bar. So, and there is also normalization here. So I would not look to this point because it makes a bit of confusion. So you can argue anything from this. Maybe we can. So assume that there is some systematic error. This could be some possible explanation, but what kind of systematic error? On the measurement of this is because you were not here this morning, so probably I should explain what I did here. One of the main, noise coming from the squid was actually one of the main candidates for this noise. And actually, to me, it was really the obvious explanation. What I did actually was the second set of points of measurement when I changed the position of the magnet in order to change the coupling. And the coupling is larger by a factor of 3, which should leads to an increase of factor of 3 of the noise because you are coupling increasing. But then I did the experiment, and well, I should explain better this because it's not so clear. If I repeat the experiment, actually, the coupling is larger, so all the points are actually roughly a factor of 3 larger than those points here. I renormalized just for the purpose of showing here. I normalized in such a way they have the same slope, and I superimposed the green on the blue. So that was that. This is just to give a picture of what is going on. But in reality, what I did was to fit the green data, the original green data, which are actually 2 factors larger, and I measured the slope and the intercept. I didn't shift, I renormalized. And what you expect is a factor of 3 larger because this should be here, basically. The green data should be shifted in such a way this intercept is 3 times larger. And this doesn't happen. So that's why I'm struggling to find a good better explanation, because if you can exclude that there's anything that comes from the squid, there is not much else if you don't do this kind of more complicated consideration on the thermal behavior, for instance, or maybe the magnetic particle can pick up some noise. That's also some option. But well, we can go back. You mentioned the systematic error. So, well, you can have systematic error. It's very, if you do very sensitive experiments like this, it's really a problem to control all the. Probably you can have maybe sometimes even simply fitting a Lorentzian curve to the high Q. Would be if you don't do that in the right way, by weighting the data in the right way, you can get into stupid systematic errors. So that's something that has to be checked very carefully before doing strong claims, of course. I'm quite confident that everything was done consistently. And in any case, well, it's really something that needs time to check all the possible effects. But maybe anybody has some other physical suggestion as a possible source of noise that can affect such a system. You are straight believing that this is CSL. So, yeah, that's for sure. You can rule out if you do something like that. Yes, that is true. Yeah, in effect, yeah, that could be a good way to exclude the CSL. But if there's anything exotic. Anything, if you cannot explain what, I mean, if you're an experimentalist, you would like to understand really what's going on in your experiment. But, well, this could be good in the prospect of a positive claim, because if you can really see something like that, with repeating many times the experiment with different parameters, you get to a single point, then you start believing in the CSL. You mean this? This is something I calculated in some numerical model by assuming that the squid is hitting the particle. So in the squid, you have this is a ring, and you have a current that flows with this Josephson oscillation, which that you can try to estimate if you like. You have a current which can be the order of the critical current, could be a few microamp, let's say 5 microamp, which oscillates in this ring. And this generates a microwave field in here. If this particle, well, if you have a microwave field there, you have some kind of dissipation. It can be due to, if it was an insulator, you can have probably a two-level system that dissipates microwave frequency. But in this case, you can have, this is just actually a conductor, so you have eddy current. So you, let's say, if you have a sphere, which is conductor, an electrical conductor, and you have a field here, which changes AC field, so a microwave field which is oscillating, then you are actually inducing an electric field which is just the shape around the field. And this will lead to dissipation, just ohmic dissipation. You can actually do, assuming that the magnetic field is actually penetrating completely in the sphere, you can exactly calculate it analytically, because you have just to divide your sphere in a collection of rings, basically, and then integrate over to the rings. And for each ring, you can just treat it as a ohmic circuit. And from this, you can calculate the dissipation. But what happens is that when the frequency becomes very high, there is no complete penetration. You have the so-called skin effect. basically the magnetic field can penetrate only a layer, which is called the penetration depth. And inside, you don't have magnetic field. You have the surface currents which are induced by the field are completely shielding the field. So that's more complicated. You have to do it numerically or using some very complicated form. But you can. What? The sphere is some neodymium. Neodymium are-boron ferromagnet, and in the magnetic at so low frequency, so low temperature. Well, I know for sure that this material has some but how does it affect the, so I know for sure that this material has some magnetic phase transition, but at much higher temperature. Yeah. How would this affect, you mean, no, but how would it explain, so here I don't see any. Yeah, no, the point that I don't see any strange transition here. I see really a beautiful linear behavior. So I don't see how this can be change anything in the system. But yeah, it's, I don't. Well, I would find strange that there is. I don't see any strange behavior in the frequency, and except this change of frequency, which is matching quite well the two-level system prediction. So there is a slow change of frequency, but it's very tiny, and it follows the more or less the qualitatively the prediction of the two-level systems. But I don't see any strange things happening. I mean, you have a transition, so what's the model? You have a transition at some temperature. Yeah. So I can tell you that if you apply the model, I don't remember the number, but if you apply this model and this power, what I got is that in the lowest point I expect 1 millikelvin of increase of temperature. And I also had another point somewhere here, but I had to exclude it because the vibration of the temperature, the thermometer was not 1 millikelvin, so which is not significant within the error bar. Okay, yeah, that's a good point. So I think this is, the lowest point is 38 millikelvin. 38. 38. So it means that you would have something like some percent of error. So you would expect actually this point to be slightly higher than but I mean Q. This is Q changes with temperature, so that's why I plot this function of T over Q, because if the Q would be constant, then I would just plot this function. Sorry, the increase of temperature, the delta T. Yeah, so yeah, but I mean here it means that basically this point should be 2 or 3% higher than this, which within the error bar basically, yeah, it is actually a bit higher. Yep. No. Okay, you want to know the temperature. Well, that could be something like I don't know, 20 millikelvin or so. I guess, but could be roughly something between 10. Yeah, so that there is there is a possible explanation according to thermology, which is the following: you have some dissipation somewhere, but that, like here, and for some reason that I don't know, the thermal conductivity is much worse than I was expecting, and the cantilever, for instance, could thermalize very well, but the particle, for some reason, which I don't know, is not thermalizing at all. Then you could have some dissipation, a small part of the dissipation, which has a saturation actually at a temperature larger than, which could be something like here. And this would be then appear just as a constant temperature here. Theoretically, you can make a model with this. Because if you have a saturation above this, you will not see it. But you still see the linear behavior because the largest part, like say 99% of the dissipation is just due to the cantilever, and it follows this. So if you want, you can find playing with the parameter, you can find a way. It sounds quite material. You want to know why I use this material? It's neodymium, it's an alloy of neodymium, iron, boron. I can give you also the precise material if you want. It's essentially the same material which is used for just the magnets you have, you can buy for $2. But it's a sphere. It's not a sphere. okay, I hope I convince you that it's not so. Even if the experiment is incredibly simple compared to other experiments like matter wave interferometry, if you want to do some precision measurement at this level, you can have a lot of troubles to control all the possible effects that can come into the system. However, it's the point is that this experiment, the most likely and reasonable sources of the effect are actually ruled out. So, if you want to really explain, you have to build a strange model and parameters which don't seem to be much reasonable. The same was for this assumption, this possible option, which was thermal noise, external noise, like magnetic field. This is as a permanent magnet. If you have any magnetic field noise that is here, you couple to this particle, and it will appear as a force. Actually, if you have a field which goes in this direction, a noisy field which oscillates, then you would have you have a magnetic moment and a field here, and then you would have a torque. So this particle would like to rotate, and it turns out that this is equivalent to have a force on the cantilever. If you calculate this force is something like the magnetic moment times the field divided by the length of this cantilever. And if you put the number, it turns out that the field noise that you need to explain this effect is way larger than what you need. Many orders of magnitude larger than what you expect in this. Well, this is actually it's not a proof because it's just a consideration based on modeling. This is not an experimental test which you can use to directly probe this. But it looks quite unlikely, so that's why I excluded this. Well, I mean, as long as I will not do any claim. This is not. I mean, this exclusion plot is safe. I mean, yeah, it is. But I mean, this is actually safe. Is a claim which I can do because I take the worst case option in which the noise is not due to CSL. So just I cannot tell anything about what is this noise. Then the maximum you can do is to draw this curve, which is no, sorry. Assuming that is the best limit I can set with this experiment is this that I can do by taking this as this excess noise is limiting my capability of bounding a CSL. If I could understand what this noise is, and for instance, it turns out that there is some weird effect which I can eliminate by playing with the experiment, then this line would go to scale to 0. In that case, this bound would actually decrease by 1 order of magnitude because now I'm off by more or less 10 error bars. So if I take the error bar as a limit, I would be 1 order of magnitude lower here. So this is not a problem. Of course, any claim related with CSL is at this moment is very preliminary because you cannot actually. The only thing you can say is that it is consistent. So far, the only reasonable explanation seems CSL actually but you can have any other kind of effect which you have not been able to find. But I like this, well, the fact that in principle it's possible if you want to just to test the CSL, then you can really do some tests like this we have discussed, and there you can really exclude that this effect, even if you don't understand what it is, you can exclude that this is CSL. Yeah. Well, yeah. If you are want to see, it's essentially the thing I told you about the experiment. You don't need to go to the end. Do you have any other question?
Questions? All right then. Thank you so much, sir. We hope that the mystery of the intercept is solved soon. And
I hope that this sits well. Sure. Just it's just no, it's just it's accidental. It's not. Well, actually, I already presented this in another workshop. But it was very preliminary. It was not even. I didn't do any other check actually, so I was not at the point that I can say that it's CSL actually. This is the first time.